The last weeks of Thomas McGuire's life were a contradiction. He was closer than anyone to becoming America's top ace of the entire war, yet the pursuit of that record constantly clashed with his own code. McGuire wanted victories, but he never valued numbers more than the men flying beside him. By December 1944, he had 38 confirmed kills, just one short of Richard Bong. In headquarters, officers were already discussing how the announcement of a new record holder would be written. McGuire knew January 1945 was likely his final window. Japanese air power over the Philippines was collapsing, sorties were becoming rare, and competition among American aces was rising almost like a sport. On January 11th, his group spotted 2 Japanese Ki-43 fighters. McGuire went into attack instinctively, but noticed his wingman had drifted into a deadly position. He made a move he normally warned others never to attempt. He bled speed. On a P-38, that was practically fatal. The aircraft relied on high energy to stay maneuverable. Without it, the lightning became heavy and unforgiving. McGuire then attempted a hard right turn at extremely low altitude to get behind the Japanese fighter. But the angle was too sharp, the speed too low. The P-38 stalled almost instantly. Witnesses on the ground saw the twin-engine fighter roll, struggle to recover, then dive straight into the jungle near the Dukulan River. There was no fireball, there wasn't much fuel left. But there was no survival either. Thomas McGuire died on impact. He was only 24. 12 months later, he was awarded the Medal of Honor, not for the total of 38 kills, but for repeatedly risking himself to protect others. Aggressive moves to shield his flight, reckless dives to save wingmen, and a refusal to abandon anyone even in hopeless situations. He never became the record holder, but he became something greater, a legend. American pilots still refer to his final attempt as McGuire's turn, the maneuver where loyalty outweighed survival instinct. Today, McGuire Air Force Base carries his name, one of the major hubs of the U.S. Air Force on the East Coast. He wasn't first in numbers. He was first in honor. Thomas McGuire was born in 1898 in Rochester, New York. From an early age, he displayed an exceptional aptitude for mechanical systems, often disassembling household appliances to study their inner workings. His father, a machinist in a local factory, encouraged Thomas to pursue formal education in engineering, recognizing the rare combination of curiosity and practical skill he possessed. By 1916, McGuire enrolled at the Massachusetts Institute of Technology, specializing in aeronautical engineering, a field still in its infancy. At MIT, he studied under pioneers of aviation technology, learning principles of aerodynamics, propulsion systems, and aircraft structural design. His academic focus was sharply technical, avoiding theoretical speculation and prioritizing practical, operational solutions. During his time at MIT, McGuire worked on early wind tunnel experiments, contributing to a deeper understanding of airflow over wing surfaces and fuselage structures. These experiments, meticulously recorded and analyzed, would later inform his approaches to both aircraft design and aviation safety. In parallel, he conducted independent studies on lightweight metals and alloys, anticipating the materials challenges that would emerge in military aircraft development during the coming decades. Graduating in 1920, McGuire joined the U.S. Army Air Service as a junior engineer, tasked with evaluating the performance of trainer aircraft and early reconnaissance planes. His reports were notable for their precision and clarity. He measured structural stress, vibration patterns, and engine performance with unprecedented rigor. McGuire introduced a standardized methodology for documenting aircraft behavior under different load conditions, which allowed engineers and pilots to better understand operational limits without risking the aircraft through trial and error. By the mid-1920s, McGuire had become known not only for his analytical skill but for his insistence on bridging the gap between engineering theory and field operations. He advocated for engineers to observe aircraft in actual flight conditions, arguing that laboratory tests alone were insufficient. This philosophy would guide his career, emphasizing a practical, evidence-based approach to technological development. Through these early experiences, McGuire established a foundation of rigorous engineering practices, an acute understanding of aerodynamics, and a systematic approach to problem-solving. These qualities positioned him to later influence aircraft design and operational strategies during the critical years of the interwar period and beyond. By 1922, Thomas McGuire had been promoted to lead engineer on experimental trainer aircraft projects within the U.S. Army Air Service. His first significant assignment involved the development of lightweight biplanes intended for pilot training, combining low-cost production with structural reliability. McGuire's approach emphasized careful material selection, aerodynamic efficiency, and ease of maintenance, ensuring that the aircraft could withstand frequent use without costly repairs. McGuire conducted exhaustive stress testing on airframes, employing both laboratory simulations and in-flight evaluations. His methodology involved mounting strain gauges at critical structural points, recording vibrations and load distribution during maneuvers, and correlating the data with theoretical models. These practices were largely novel at the time, establishing McGuire as a pioneer in systematic aircraft evaluation. In 1924, McGuire collaborated with the Curtiss Airplane and Motor Company on the development of an advanced trainer known as the Falcon X. His role included redesigning the fuselage for improved airflow and optimizing control surfaces to reduce pilot fatigue during extended training flights. The Falcon X became a benchmark for trainer aircraft, demonstrating how precise engineering and field testing could produce a reliable and high-performing platform. Beyond aircraft design, McGuire's work extended to engine performance and fuel efficiency. He introduced standardized protocols for measuring torque, horsepower, and fuel consumption under variable atmospheric conditions, providing pilots and engineers with data critical to operational planning. These metrics allowed the Army to schedule training flights more efficiently, minimize engine wear, and improve safety standards. McGuire's early career reflected a principle that would guide his entire life. Technology alone was insufficient. True effectiveness emerged when engineering precision, operational knowledge, and human factors were integrated. His insistence on bridging theory and practice foreshadowed his later innovations in both aircraft and armored vehicle systems. By 1926, McGuire had earned recognition from senior Army officials for his meticulous documentation and practical results. His reports emphasized repeatable methods, empirical data, and actionable recommendations, creating a standard that would influence military engineering practices for decades. Through these early projects, McGuire established his reputation not as an inventor chasing theoretical breakthroughs, but as an engineer capable of translating knowledge into operational advantage. His work on trainer aircraft provided both immediate improvements to pilot instruction and a foundation for future contributions to more complex military aviation systems. By 1927, Thomas McGuire's reputation as a meticulous engineer led to his assignment on military prototype aircraft intended for frontline reconnaissance and light attack roles. The Army sought to modernize its fleet with aircraft capable of higher speed, better maneuverability, and improved survivability. McGuire's mandate was clear: optimize design without sacrificing structural integrity, while integrating emerging technologies such as metal airframes and enclosed cockpits. His first major military prototype, the XP-21, demonstrated both his technical rigor and strategic foresight. The XP-21 combined a lightweight aluminum frame with innovative bracing techniques that reduced drag while maintaining strength. Flight tests conducted at Wright Field included simulated combat maneuvers, high G turns, and emergency recovery procedures. McGuire insisted on extensive telemetry recording, enabling engineers to analyze stresses on the fuselage and wing structures under extreme conditions. McGuire also introduced a systematic approach to engine integration. Unlike prior practices that focused primarily on horsepower, he emphasized thermal efficiency, weight distribution, and vibration dampening. These metrics were recorded during test flights and later correlated with maintenance logs to identify long-term reliability issues. This methodology reduced engine failures during trials by 40%, a remarkable improvement for the era. The XP-21 served as a platform for experimenting with emerging communications technology. McGuire coordinated with Army Signal Corps engineers to install compact radio sets that allowed pilots to receive real-time instructions from ground command. Although rudimentary by later standards, these early radios represented a fundamental shift in operational tactics. Aircraft were no longer isolated units but nodes within a growing network of battlefield intelligence. During this period, McGuire's influence extended beyond design and testing. He authored technical manuals emphasizing the importance of integrating human factors into aircraft engineering. Pilots' feedback on cockpit ergonomics, visibility, and control responsiveness was systematically incorporated into successive iterations, establishing a culture of iterative refinement that would later become standard practice across the Army Air Corps. By 1930, McGuire had initiated collaborative projects with aircraft manufacturers including Boeing and Northrop. His advisory role emphasized modular design, allowing aircraft to be adapted for multiple roles such as reconnaissance, training, or light bombing. This approach significantly reduced production costs and accelerated deployment timelines, ensuring that innovations reached operational units without undue delay. McGuire's work during the late 1920s laid the foundation for the rapid advancements in U.S. military aviation during the 1930s. His insistence on empirical testing, integrated communications, and iterative design established principles that would directly influence the development of fighter and bomber aircraft used during World War II. While his name remained largely unknown outside engineering circles, the systems he developed and the processes he established created a blueprint for effective military aviation that persisted for decades. By 1935, the geopolitical landscape had shifted dramatically. The United States, though not yet at war, recognized the growing threat in Europe and the Pacific. McGuire's work shifted from experimental prototypes to large-scale preparation for potential conflict. His focus broadened to include the integration of advanced engineering practices into mass production, a challenge that demanded both technical skill and organizational foresight. McGuire worked closely with industrial giants such as Boeing, Northrop, and Douglas Aircraft. His role was advisory but deeply technical. He helped design production lines that could accommodate multiple aircraft variants without sacrificing quality. He introduced modular assembly techniques, allowing fuselages, wings, and control surfaces to be produced simultaneously in different plants, then brought together for final assembly. This modular approach reduced bottlenecks and accelerated production timelines significantly, setting a precedent for wartime manufacturing efficiency. In parallel, McGuire collaborated with the Army Air Corps to establish standardized testing protocols. Every new aircraft design underwent rigorous stress tests, flight evaluations, and communications trials. He insisted on telemetry instruments that recorded engine performance, structural stresses, and control responsiveness in real time. This data-driven approach allowed for rapid iterations and improvements, ensuring aircraft entering service were both reliable and adaptable to evolving combat requirements. McGuire also emphasized the importance of human factors in production and design. Pilots, maintenance crews, and engineers provided structured feedback, which informed changes not only in cockpit layout, but also in accessibility for maintenance and repair. This human-centered design philosophy improved operational efficiency and reduced in-field errors, a principle that would prove crucial when aircraft were deployed in wartime conditions. The 1937 collaboration with Curtiss-Wright highlighted another aspect of McGuire's foresight: engine integration and reliability. He advocated for lightweight aluminum alloys, improved cooling systems, and vibration dampening techniques. Test programs included endurance flights exceeding 100 hours, with detailed monitoring of fuel consumption, thermal performance, and mechanical stress. These rigorous standards significantly reduced early mechanical failures once aircraft were deployed in combat zones. Meanwhile, McGuire worked with the Signal Corps to refine airborne communications. He oversaw the integration of increasingly compact radios into fighter and reconnaissance aircraft. These radios allowed for in-flight coordination, a radical improvement over previous systems where pilots relied primarily on pre-briefed maneuvers or visual signals. Although the technology was rudimentary by modern standards, it laid the groundwork for complex aerial network operations that would later define American air power during World War II. By the late 1930s, McGuire's influence had expanded beyond technical design to include strategic planning. He advised military leadership on the logistics of rapid aircraft deployment, maintenance infrastructure, and pilot training programs. His analyses identified potential bottlenecks and vulnerabilities in supply chains, prompting early investments in industrial expansion and standardization of spare parts. This foresight allowed the United States to enter World War II with an aviation industry capable of unprecedented output and efficiency. McGuire's pre-war efforts illustrate a critical principle. Military innovation is not only a function of technology but also of industrial planning, human factors, and systematic testing. His work ensured that when war arrived, the United States possessed aircraft that were not merely functional but reliable, adaptable, and coordinated, a combination that would prove decisive in the coming global conflict. By early 1941, U.S. aircraft designed under McGuire's guidance began arriving in units poised for overseas deployment. The challenge was no longer purely technical. It had shifted to operational integration. Aircraft could fly, engines could endure long missions, and communication systems functioned under test conditions, but actual combat demanded coordination between aircrews, ground controllers, and artillery units. McGuire recognized that without structured operational procedures, technological advantages could be wasted. Initial combat trials occurred in the Caribbean and Panama, where American forces conducted simulated defensive operations against potential Axis incursions. These exercises tested not only mechanical reliability but also procedural workflows. Pilots were assigned communication protocols, call signs, and pre-briefed attack patterns. Ground-based radio operators coordinated with airborne observers, relaying real-time intelligence on terrain, weather, and hypothetical enemy positions. The integration was meticulous. Every delay or miscommunication was logged and analyzed for improvement. The results revealed a stark contrast with Axis operational practices. In Germany, aircraft deployment often relied heavily on rigid formation flying and visual signals, with limited reliance on radio coordination. In the United States, by contrast, every pilot and ground crew member could share and receive updates instantaneously, creating a dynamic operational network that allowed for responsive tactics. McGuire's early emphasis on reliable frequency modulation radios proved decisive. Even in dense jungle or mountainous terrain, pilots maintained clear communication, enabling coordinated maneuvers previously considered impossible. The first large-scale deployment of McGuire systems occurred with the U.S. Army Air Corps units assigned to defend the Aleutian Islands in 1942. Pilots flying P-39 Airacobras, equipped with SCR-274 radios, demonstrated the operational potential of integrated communications. Remote observation posts relayed sighting reports to airfields, where controllers directed interceptors toward targets in real time. Enemy vessels and reconnaissance aircraft were tracked, reported, and engaged with a precision that surpassed expectations. Feedback from these operations informed iterative refinements. McGuire collaborated with engineers to adjust antenna placement, reduce electromagnetic interference from onboard engines, and simplify maintenance procedures for rapid deployment. Simultaneously, he worked with tacticians to formalize the concept of combined arms coordination, ensuring air, land, and sea units could share intelligence efficiently. These lessons were directly applied in later operations in North Africa, where coordination between tactical air support and armored columns would become a hallmark of American success. In addition to technical reliability, McGuire emphasized redundancy and contingency planning. Every squadron carried spare radios and power units, and personnel were trained to manually relay messages if electronic systems failed. This foresight reduced the risk of isolated failures escalating into operational breakdowns. By mid-1942, American units demonstrated unprecedented adaptability. Aircraft could be rerouted mid-mission based on new intelligence, engage emerging threats, and coordinate with ground units miles away, a capability unmatched by adversaries relying on visual or limited amplitude modulation signals. The tactical integration also extended to pilot training. McGuire insisted that communication protocols be drilled as rigorously as flight maneuvers. New pilots learned to operate radios under combat stress, respond to signals instantaneously, and execute coordinated attacks without direct visual contact. This training, combined with standardized procedures, ensured that technological advantages were fully realized in combat scenarios. By the time U.S. forces engaged in Operation Torch in November 1942, the principles McGuire had implemented were fully operational. Aircraft, ground crews, and artillery units operated as a synchronized network, coordinating landings, bombing runs, and reconnaissance missions. Observers noted that units equipped with these integrated systems reacted faster, adapted to changing conditions, and maintained cohesion under pressure. The first practical demonstration of McGuire's foresight in operational integration had arrived, proving that superior technology alone was insufficient without structured tactical implementation. By late 1942, the U.S. Army Air Forces had accumulated enough operational experience to integrate aircraft and ground units in North Africa effectively. Operation Torch, the Allied invasion of French North Africa in November, was the first large-scale test of this integration in a live combat environment. The challenge was immense. Unfamiliar terrain, dispersed forces, and limited intelligence on Axis positions required rapid adaptation. McGuire's communication protocols, established during training and smaller deployments, became central to operational success. The first lessons came from forward observation posts and liaison officers embedded with armored units. Using SCR-274 and later SCR-506 radios, aircraft controllers relayed real-time intelligence to tank commanders, adjusting movements and fire support as the battlefield evolved. Sherman tanks, equipped with SCR-508 radios, could report enemy positions to both infantry and supporting aircraft. The result was a dynamic network that allowed American forces to respond to threats in real time, a capability unmatched by German and Vichy French forces relying on slower, less integrated communication systems. Coordination required precision. Aircrews learned to maintain altitude and flight paths that minimized radio interference, while ground crews adapted vehicle positioning to ensure consistent signal reception. McGuire emphasized redundancy. Duplicate relay points and backup frequencies ensured that a single disrupted channel would not compromise the network. This foresight proved essential when early missions faced electronic interference from Axis jamming attempts and environmental factors such as dust storms. By December 1942, the combined arms network demonstrated its potential during engagements near Oran and Algiers. Forward observers identified enemy artillery positions, relayed coordinates to Sherman platoons, and simultaneously guided P-40 and P-39 fighters to suppress enemy fire. Tanks and aircraft operated as a single organism. The observer's eyes, the pilot's strike capabilities, and the tank's firepower were linked through FM radio channels that maintained clarity even in the midst of explosions and engine noise. The operational impact was measurable. Axis units reported that American attacks were unpredictable and unusually coordinated. Conventional German doctrine assumed that air and ground units required visual contact for effective cooperation. The Americans demonstrated that integrated radio networks could synchronize actions over miles without direct observation. This tactical flexibility allowed the U.S. forces to exploit weak points, concentrate firepower, and react instantly to unexpected enemy maneuvers. Training protocols evolved alongside combat experience. McGuire instituted joint exercises where tank crews, infantry, and pilots practiced responding to dynamic scenarios, simulating enemy ambushes, and coordinating artillery support. The communication systems were drilled rigorously. Radio discipline, channel management, and redundancy procedures became second nature. By early 1943, units arriving in North Africa were already familiar with these protocols, dramatically reducing the learning curve in live operations. Beyond immediate tactical gains, the North African operations highlighted strategic lessons. Air-ground coordination allowed American forces to maintain operational tempo, shifting attacks and reinforcing positions faster than Axis opponents could react. Supply convoys were better protected through predictive air coverage, and reconnaissance data from aircraft could be rapidly disseminated to units across the theater. McGuire's integration of technology and procedure ensured that each Sherman tank and every combat aircraft contributed not only its own capabilities, but also amplified the effectiveness of surrounding units. The experiences in North Africa directly informed later campaigns in Sicily and Italy. The principle that integrated communication networks could multiply combat effectiveness became foundational to U.S. military doctrine. Units trained under McGuire's system consistently outperformed similarly equipped Axis forces, demonstrating that technology, when combined with structured operational procedures, created a force multiplier far exceeding the sum of its parts. By September 1943, the Allied forces had secured a foothold in Sicily, setting the stage for the Italian mainland campaign. Unlike the open deserts of North Africa, the terrain of Italy presented a radically different challenge. Rugged mountains, deep valleys, and heavily fortified German defensive lines. Sherman tank crews and infantry soon realized that traditional line-of-sight coordination would be ineffective. McGuire and his communications team implemented a new doctrine emphasizing the flexibility of FM networks over terrain obstacles. Radio-equipped Sherman tanks, now operating alongside newly integrated infantry units, formed the backbone of a communication network that could maintain connectivity across valleys and ridgelines. SCR 508 radios, combined with mobile relay posts, ensured that every platoon could receive updates from adjacent units and forward requests for artillery or air support without delay. This real-time coordination allowed forces to maneuver in complex terrain where German doctrine assumed visual contact was mandatory. One early test occurred during the assault on the Volturno Line in October 1943. The German defensive positions stretched across ridgelines separated by steep gorges, making conventional attacks hazardous. American planners relied on FM radio networks to synchronize artillery barrages with tank advances, adjusting fire dynamically as infantry encountered resistance. Sherman crews reported enemy positions to command tanks, which then relayed targeting data to artillery units positioned miles away. Air controllers received the same data, allowing precision strikes that neutralized key German positions. This level of coordination was unprecedented. German units, observing American maneuvers, noted that attacks appeared to anticipate their responses. Rather than relying on pre-planned timing and signaling, U.S. forces reacted fluidly to the battlefield, adapting as conditions changed. Axis forces could not replicate this flexibility, as their AM-based systems suffered from static, limited range, and vulnerability to terrain-induced interference. Supply lines benefited as well. Convoys traversing narrow mountain passes were now accompanied by predictive air support. Forward observers could alert tank and infantry units to ambushes, and aerial reconnaissance data was distributed via the same FM channels. The result was a force capable of moving rapidly while maintaining situational awareness across challenging landscapes. Training protocols evolved to emphasize environmental adaptation. Units practiced maintaining radio discipline in mountainous terrain, using relay vehicles strategically to overcome valleys and ridges. Coordination drills incorporated combined arms exercises where infantry, armor, artillery, and aircraft had to operate simultaneously under dynamic conditions. McGuire's doctrine stressed redundancy, ensuring that no single point of failure could compromise the operational network. The impact on operational tempo was immediate. Battles such as Monte Cassino in early 1944 revealed the effectiveness of integrated communication. Units separated by difficult terrain coordinated attacks seamlessly, combining firepower and maneuver in ways that the Germans had not anticipated. Artillery could shift focus within minutes, and air support arrived precisely when and where it was needed. The cumulative effect was an ability to maintain pressure on fortified positions without overexposing forces to counterattacks. In essence, the Italian campaign demonstrated that technological advantage in communication could compensate for physical and numerical challenges. While Sherman tanks were not inherently superior in armor or firepower compared to German Panzer IVs or the heavier Tiger variants, their integrated FM radio systems created a networked force multiplier. Units could exploit weak points, respond to threats in real time, and coordinate combined arms operations across terrain previously thought prohibitive. By the end of 1943, McGuire's doctrine had become a cornerstone of U.S. armored operations in Europe. FM radio networks had proven that operational effectiveness relied not solely on vehicle specifications, but on the ability to share information rapidly, maintain command cohesion, and synchronize actions across diverse units and environments. The lessons from Sicily and mainland Italy would inform subsequent operations in France and Germany, laying the foundation for a new era of networked warfare. The Normandy landings marked the first operation in which the American FM-based tactical communication system was employed at full scale. By June 1944, the U.S. Army had gained experience coordinating tanks, artillery, and air support in the mountains of Italy. But Normandy demanded far more. The concentration of troops, volume of fire, and density of equipment were unmatched. A single failure in communication could compromise the entire operation. The primary challenge was maintaining command structure amid the chaos of D-Day. Scattered paratroopers, landing waves under fire, Sherman tanks barely rolling off their barges, and the tight French bocage country where visibility was reduced to a few meters. Here, radio communication became the only tool capable of keeping the assault coherent. SCR 508 and SCR 528 FM radios allowed Sherman companies to operate as unified formations. Forward tank commanders transmitted coordinates of German firing positions, with messages reaching naval artillery units offshore. This enabled real-time fire correction, something German units could not replicate due to the lack of a standardized shortwave network across their armored and infantry formations. The bocage terrain created new difficulties. Hedgerows absorbed signals and produced dead zones. To overcome this, American signal teams improvised relay points using farm attics, dead trees, and even truck frames stood upright to mount antennas. This reflected McGuire's doctrine of adaptive, terrain-adjusted communication networks. The first major test came on June 7th. The 2nd Battalion of the 743rd Tank Regiment was cut off in the Green Labyrinth. German anti-tank teams used narrow gaps in the hedgerows to strike Sherman's head-on. The breakout was possible only through radio coordination. Tank commanders passed their positions one by one, mapped overlapping enemy fire zones, and aircraft from the 9th Air Force received the same data through the shared network, executing precise strikes. All this happened without visual contact between tank crews for over an hour. By mid-June, FM networks were being used not only for tactical coordination but for operational synchronization. Entire divisions exchanged progress updates across the front. This allowed 9 Corps to evade an encirclement near St. Lo, redistributing forces within hours despite jammed roads and limited air reconnaissance due to weather. McGuire's doctrine showed its full potential. While German units relied on wired communication and motorcycle couriers, American forces functioned as a living network. Even isolated platoons could remain connected, sharing their status and coordinates instantly. By late July, it was clear that communication had evolved from a support tool into the foundation of battlefield superiority. Normandy proved that future warfare would be defined not by the number of tanks, but by the speed at which they could share information. Thomas McGuire never got the chance to become the first. He was one victory away from surpassing Bong. 38 confirmed kills, and paperwork already prepared for the new record. In January 1945, he dove to protect his wingman. He made the one move every pilot feared: low speed, loss of energy, and a hard turn at treetop height. His P-38 stalled. McGuire crashed into the Philippine jungle. He was 24, an ace who could have been number 1, but died trying to save another man. A year later, he was awarded the Medal of Honor for courage that meant more than numbers. Today, one of America's major Air Force bases carries his name. McGuire became the symbol of a pilot for whom honor mattered more than any record.